In this video, we'll move into section 8.2 and we'll discuss surface area for solids of revolution. Now, this can be a pretty difficult section because we can treat this very similarly to the volume problems that we did at the beginning of class in chapter 5. And as we saw back then, if we revolved our figures around either the x or y axis, that would typically be a lot more friendly than if we revolved around, say, a line y equals 4 or x equals 2 or any of those other lines. So that's kind of the same thing we'll see here. And we mentioned in the chapter 5 videos, if we always limited ourselves to only going around the x or y axis, we could simplify those formulas a little bit. What is the R value? And, we can make some more definitive statements. But because we had those other possibilities, we had to be a lot more flexible. We had to draw a good picture so we could always visually see what was happening. But now I say all that, and we could do similar things in 8.2, but we're not going to. This is actually going to be a very quick section as we just show one more general application for definite integrals. So we started off with area, then we move three-dimensionally, talk about volume, then we jump back to two-dimension and talk about the length of curve, and now we're back to three-dimensional talking about surface area. These are ways some people might be curious, how do we have some of those formulas for like the volume of a sphere or the surface area of particular figures? Some of that was known beforehand and was proved through calculus. Others were entirely, the calculus was the origin of those formulas. But again, we're not going to get too deep into that. Let's take a nice look at this section. So what I'm going to do, like we do in so many other places, let's start off with some basic picture. Here's some function f of x, and let's trap this figure from here, here, and let's keep it simple. Let's go to the x-axis. So that would be my trapped region. Let's revolve around the x-axis. And that would be our three-dimensional shape. It's not exactly a drum or a barrel. It kind of bulges out in its sides here. If you turned it sideways and looked at it this way, again, maybe it's a little bit more like a flower pot, especially if I change it this direction, the base of the pot to the top of the pot. We've seen some of those fancy ones that both sides bulge out, things of that nature. So that's the type of figure we're looking at. And we're not worried about, is it empty, is it solid? Again, we're going to keep this pretty generic. So I want to think about surface area. Well, it's not quite simple. So what we're going to do, like we do in so many other situations, I'm going to chop this, think of this as a bunch of sections, and think about peeling an individual section. So if I made a little slice on the x-axis and unpeeled this, that would be one, again, I'm thinking surface area. I'm not worried at all about volume here, just thinking about. That's why it looks similar to the peel technique, but it's not exactly the same. That if I have this figure, if I put a slice in it and open it up, that's the kind of thing we're doing here. So I put my slice on the x-axis, open all of these up. This piece of area plus this piece of area plus this piece of area plus this piece of area would give me the surface area of the entire figure. Now again, I'm kind of skating through this. We would technically have to do this an infinite number of times. Technically, while we're only doing 4, we'd be flattening off these sides. So that way when I unpeel these, I'm getting these nice little sheets of paper. So unravel this, and I'd get this. And then unravel this, and I'd get a longer piece, and so on. I want the area of this. The area of this flat piece of paper wrapped around would represent the surface area of just this portion. And again, we're going to add all those pieces together. Well, this side, the area of this is just a simple base times height. length times width, base times height, whichever way you prefer to see it. the base itself from here to here, from here to here, from here to here. That's our traditional delta x. I'm sorry, that's not exactly correct here. I'll come back to that in a moment. Let's start with the first, this distance, the height. The height of this strip would really represent the circumference of the initial circle. So we're going to get a 2 pi r, where the r value would be the y value on the curve. So 2 pi r, this is where I was saying, if we were not always just going around the x-axis, that's where we would just leave it as an r, and we'd have to look at each individual picture like we did with volume. Well, here the r is from the x-axis to the curve, the y value on the curve. You know, we're still doing this overall in terms of x, so I need my function in terms of x, and that would end up being, in this example, the f of x. But if this was the line y equals -1, we'd have to do the curve plus 1 and all those other adjustments. But like I said at the beginning, we're not doing that here. So that allows me to just do that as 2 pi f of x. Some people would prefer to write 2 pi y. The other piece, the base, I did that a little too quickly, everybody. The base would be this distance, but really it's this. As we cut it down more and more, it's not going to be straight. We're going to need this distance. This distance is the arc length. It is the length of curve. So we saw that in 8.1, and we put all of that together. Again, this is just one piece. I'm really skipping. In 8.1, it wasn't a formal proof, but we really went through all the steps and the reminder of a definite integral. Here we're going even faster still. I'm just cutting it down. I mean, really, we do the summation of this times this. Why not just do it? So the summation of base times height, most people just tend to write this part in front of the square root part. And technically, this would be a delta x at this point. Again, I kind of left that at the end. I had the dx up here. The dx is kind of a part of this. We're taking that limit as we make an infinite number of cuts. That will give me the surface area. So that summation as n goes to infinity becomes the definite integral. Again, if you still want to write that as y or f of x, if you write that as a y, then you typically write dy over dx quantity squared here. If you have it as an f of x, you typically write f prime of x, quantity squared here. Okay, so there's my formula, and that's really the point. Same thing in 8.1. This formula is even worse than what we saw with arc length in 8.1. We have to be very fortunate to have a function that we could plug in and just get a nice answer and be able to solve. So a lot of the homework here, and there's not too much homework, but a lot of the homework is just about setup. Set up an integral that represents that surface area. The only little thing that they also point out, if you went around the y-axis, well, it just flip-flops. It becomes 2 pi function of x in terms of y. So 2 pi x, and x could be treated as g of y. And then this would be a derivative in terms of y. G prime of y quantity squared, or dx over dy quantity squared instead of dy over dx. So same basic formula, but now let's solve one. Let's find the surface area of the figure generated by revolving the trapped area Let's do y equals, let's keep it simple. Let's do y equals x squared from x equals 0 to 1. There's my function. Again, y, f of x, whichever way you want to treat it. There's a, there's b. The only thing missing for the setup is that I need the derivative. So all this was given in the problem. That's really the only work I've done so far. surface area, 0 to 1, 2 pi times the original function, 1 plus, 1 plus the derivative squared. And this is still not really that nice of a function, right? We still look at this, and it's still not really all that good, because even though we could solve this one, it's still not a quick, easy U-sub. You could make it work as a fancy U-sub, everybody. This is one of those problems, and that's why I wanted us to see this. There's nothing scary about this problem. This looks very, very friendly, but it still doesn't work out particularly nice. So, just to point out, how would you solve this one? You'd have to do, this is one where at least you could do a trig sub. You've got the square root. You'd have to manipulate this a little bit. Some people factor out a 4, a few little variations. But this could be your a squared plus x squared form. Use a trig sub. Some people might get a little lucky with something like this and realize, well, 1x cancels, but then, can I do something else? It's not really very good. The trig sub is much better. So this did not look bad at all, but still led us to basically an integral that would be really, really hard to solve. So let's just take that one step further. I don't mean make it harder. Let's show you one that does work. And all we have to do, let's make that an x cubed. Now the derivative is 3x squared. So now that's a 9x to the 4th. This is an x cubed. And now we're lucky. And like I said, make sure you notice I made that change. Initially with the initial problem, didn't look bad, but we still saw it was tough. So I kind of, just changed the directions to just say set up, and then we were done. But now I changed the problem, and now I do want us to finish solving this one, because this one will work. This one, multiplication, all this times this. Don't let the 2 pi bother you. You can kick that out in front if you want. But the x cubed times this radical. But here we've got inner outer. If we again try u as the inner, finally we'll get something nice. Here we're still mentioning only 1x cancel, still a bear. So that's why, again, a trig sub would be the better way in the original. But now this one will actually work. 2 pi still there, x cubed hanging out. That's now u to the 1/2 power. dx became du over 36x cubed. Now I know my u sub is truly working. That canceled. All I have left is u. Still a little mess. 2 pi over 36. A pi over 18 out in front. The anti of u to the 1/2 is u to the 3/2 times 2/3. And now I'm just finishing up with a little cleanup and back sub. Back and reduce. So I've got a pi over 27 times the quantity 1 plus 9x to the 4th to the 3/2 power from 0 to 1. And now plugging in. Pi over 27, plug in 1. You get 10 to the 3/2 power minus pi over 27. You plug in 0. You get 1 to the 3/2, which is 1. And that's, again, about as good of an answer as we can get. You still can't do much with the 10 to the 3/2 power unless you use a calculator, and then you're just getting decimal approximates. Okay, everybody, so that's basically it. We saw one problem that did work, one problem. Again, it's not up to you. I would, in the directions in your homework or on a quiz that goes with this, again, be very clear. Find the surface area. Here's the setup. We had to keep going and solve. But let's just do one more that just says setup. Set up an integral that represents the surface area of the figure generated Actually, I just realized one quick little thing. I also have to include y equals 0 here, right? To make sure this trap region, notice I never drew a picture. I'm really leaning on the formula. I drew the picture here to develop this formula, but now I could just go right in, but I do also need y equal x cubed, y equals 0, x 0, and x equals 1. That gives me my fully trapped region. So same thing here. Find the area of the figure generated by, let's have e to the tan x minus inverse tan of 3x plus 10x. And let's go from x equals -1 to 3. Now this looks pretty ugly, but all we're doing is setting up the integral. So I already have my original y, the derivative, I did that a little quickly, but that's an e to the u du. Inverse tan u, 1 over u squared plus 1 times du. So I just did that a little quickly, but all that work, this looks pretty ugly. You plug in your surface area formula, 2 pi, all of this mess, all times the square root of 1 plus this derivative squared. And I hope you're realizing the setup, it's not hard. It's just making sure you don't miss anything. And it just took up a lot of space. So just to see it, there's my a and my b, 2 pi times y, square root 1 plus y prime squared, and even the dx. You talk about setup, the dx or dy is just as important as any other piece, and especially if I'm only asking you to set up, if you forget the dx or the dy, or forget the bounds, it seems like those are quick, easy things, but forgetting that is a major mistake when all you're being asked to do is set up. So definitely don't miss that. Let's make sure this is a good, easy section. Thinking about the quiz that covers this material. Again, 7.8, that's definitely the big focus on the quiz. Much more time spent in the videos, much more homework, a lot of concepts involved. So that's a big part of your quiz. 8.1, 8.2, just a little bit. 1, 2 problems. Maybe they're set up, maybe they're solved, but not too much from that.